Welcome. Today I will be solving Leetcode hard problem number 269, alien dictionary, and I'm going to show you two different solutions of how to solve this problem. One, using Kahn's algorithm, BFS with a Q. Two, we're going to use DFS with recursion and visited array or hash map. Let's get started. So I would like you to read this dictionary problem description first. So 269 alien dictionary. But the basic concept of this is there's a new alien language that uses English letters or alphabet. However, we don't know the order of this letters, how they group their letters. But we're given a list of strings, words from alien language dictionary, and this is the important part, where the strings in words are sorted lexicographically by the rules of the new language. So that means, for example, if the word is W and that next one is ER, we know that W comes before E. Return a string of unique letters in this new alien language in sorted lexicographically increasing order by the new language rules. If there is no solution, return an empty string. So they provide a few examples here, but let me turn on my iPad and explain it to you. First, for this problem, you need to understand the concept of directed graphs. Directed graphs have edges, so what we need to do is we look through all the words here and compare them one by one. So we know that WRT and WRF, they both have same first two letters, so that doesn't give us any information. But here we see that T comes before F. So we create an edge from T to F. Next, we look at WRF and ER. W and E are two different letters, and we know that W comes first before E because this word appears before ER. So we link W and E. W has an edge to the E. Then we check ER and ET. The first two letters are exactly the same, but the next two letters are different. So we link R and T because R comes before T. Then we look at the last two words, and obviously E comes before R, so we link E with R. So we need to understand the concept of how to build this graph. The next concept you need to understand is topological ordering sort. So what that means is for each directed edge from node A, in our case, let's say W, to node B, E, here, node A appears before node B in the ordering. So we know that W must come before E in the alien dictionary. So the way we can do a topological sort is using Kahn's algorithm, BFS, or use DFS. I'm going to show both solutions. Let's start with Kahn's algorithm. To do Kahn's algorithm is we need to process all the letters and build in-degree hash map. It will all start with initially with zeros, and then once we create a graph, once we create a link such as W to E, we know that E has one edge leading to it from W, so we'll increase it and set it to 1. Same thing from T to F. F has one edge, T has one edge, R has one edge. W has 0 edges because nothing is linking to it. So the way Kahn's algorithm works is we create in degree with all the edges, and then we push on the queue the letter that doesn't have an edge to it, which would be W. Once we push the W, we process it, add it to our result. We got rid of the W, so all the edges it's pointing to, such as E, we decrease it and set it to 0, and everything that's set to 0 gets pushed in the queue, and we process it again, and so on. So for example here, we have WEF, so we have an edge from W to E, so E is 1, from E to F, so F is 1, nothing points to W, so W is 0. So the way it would work is the queue first would get W. Once we pop it, we get rid of it, add it to result, decrease all its neighbors by 1, so this will become 0. And then we add to the queue all the edges with 0 again. So it will be this one. We add it to the result. Let's say we have result W. We pop it, E, add it to result. And now F has 0 edges link into it. So then we put the F on the queue and add it to result again. And that's it, we're done. So that's how Kahn's algorithm works. The only other thing to know is we need to be able to detect cycles. This is a cycle right here. So in this case, every node has at least one edge. So we cannot put anything in the queue to process. So that means there's a cycle. Now let's get into some code. I'll keep the iPad open here so you can reference this code. And yeah, let's start writing code. So the first thing we need to do is we need to create a graph. We'll use a hash map for that. We'll keep a track of all our letters. So the key will be letters such as W, and it will have a set of letters of edges. In C++, a hash map is an ordered map, and a set is an unordered set. And then we'll create our in degree hash map that will have the letter and the count. Then we need to process every single word and letter. So let's go through each word and let's go through each letter. Character in the word, and then we'll populate our in degree. Initially, we'll set it to 0. Then we'll start comparing all the words. The first thing we need to do is get our word size, and we'll start looping through all our letters up to n size -1, because we're comparing pairs when the first word and the second one, and then so on. So once we reach the end, it's going to be out of boundary if you try to grab the next word. So we want to go up all the way to W size -1. So the next thing we do is let's get word 1, which is going to be at our index I. We'll get word 2, which is going to be at index I +1, the next letter. Then we'll get the minimum length of each letter, of each word, because there might be a case where letters are different size. So we cannot just compare if the word is A, B, and the next one is C. If you try to loop through 3 letters, it's gonna fail because the second word only has 1 letter, right? So we need to get a minimum size and loop through that instead. And if those letters don't equal to each other, then we know we have 2 letters that don't match. So the first thing we need to check, does that letter already exist as a value in our W1J key? So let's extract current letters that are already in our W1J. So for example, on the iPad here, you can see that W will link to E. So we're checking, does W already have E or not? So if it doesn't, if we don't have that letter in our hash map yet, then we'll insert it into our word 1 index J. Let's say it's W, for example, and we're inserting E, letter E. And then since we have an edge to W to J now, we also need to increase our in degree. And we only want to compare the first letters. So we break after that. If they don't equal, we compare and then we break. Because that's the only thing that gives us information about letters. We only care about the first letters that do not match in the words, basically. And then we break. So the next thing we need to do is we need to create a queue, and let's go through our in degree and push into the queue all our keys that have value 0. So in C++, in degree is a hash map. Pair first is going to be the key. Pair second is going to be the value. So if the value is equals to 0, then we'll push that key into the queue because we know it has 0 degree in degree. So then the next thing is, like, let's say we set up our resolution, which is an empty string. We return it here. But next thing we need to do is process the queue. So while queue is not empty, we pop the character that's on the queue. We access the character in the queue, then we pop the queue. Then we add that character to our solution, which is res. And then we go through all the letters neighbors. So for example, for W, the neighbor is going to be E in our example. And then, since we already popped CH here, and our example is W, we need to decrease the in degree of the neighbor. And if that neighbor becomes 0, then we can also push it on the queue to process next. All right, and that's it. We're done. The only thing is that's left, we need to check for cycles. So to detect a cycle, we know that all the in degree should become 0 in value after we're done. So if some in degree value is more than 0, then we'll return an empty string. Another way to check the cycle is by checking if our resolution size is not equal to in degree size. Then we can also return this, because in degree will have every letter. So if our solution doesn't have some letter and the size is not equal to in degree size, then we know there's a cycle or something went wrong, so return empty as well. But let's use the first one, right? So let's run this code in Leetcode. First run it for the test case, and it passes. So now I'm going to submit it, but it's not going to pass, and I'll tell you why. There was a description here before that's not here anymore, it seems like, that we also want to check for prefixes. Now, what is a prefix? The example that failed here is AB and ABC. Prefix is if there's a letter, if there's a word that's a prefix of the word before. So AB is a prefix of ABC. So we should return in that case empty string. So we just need to add one more condition, special case, where we check for prefixes. So if size 1 is bigger than size 2, sorry, I need to do it here once we extract the words. So if size 1 is bigger than size 2 and we can find word 2 in word 1 at index 0, then it's a return empty string. So for example, if word 1 is ABC and word 2 is AB, size is bigger, 1 than 2, and then we can find W2AB, it's at index 0, so we know it's a prefix. So now that I added this condition, let me run this code again. Boom, done. Okay, that's how we solve it with BFS, Kahn's algorithm. Now let's do it with DFS. Let me reset this code. Let me copy this function again. But this time in this code alien order, let me add 2 here. So we can have a unique function for DFS, alien order. All right. So now let's do it the DFS way. Now, some of it is going to be kind of similar and some of it is going to be really different. So the first thing is we still need our graph array, hash map, and not in degree, but we need visited state. Because when we do DFS, we need to know if we visited that node already or not. So we're going to have 3 states for visited based on the character. Let's say the character is W. If we didn't visit it yet, then it's 0. If it's 1, that means visiting, and we're currently visiting it. And if we access it again and it's in that state 1, that means there's a cycle. It's just standard DFS cycle detection. So if you don't know how to do that, you need to read it up. And then finished visiting this state 2. All right, so we have visited array. Also, a good interview tip is add some test sample checks, such as, for example, if the words array is empty, we should also return empty string. All right, so if the words array is empty, then we return empty. So once again, we need to process all the words here. And if we cannot find that letter in our visited array, then we set it to 0. All right, so we basically, what we did is we went through every letter and we decided to set it to 0 because we haven't visited any of the nodes yet. So then the next thing we're gonna do is we're gonna process all the letters and words again and compare them to each other. So let's get the size and then start processing. String 1, W1. Let's get the first word. Let's get the second word. Let's include our condition for the prefix as well, so we don't forget that. So this code is going to be kind of the same, but instead of copying pasting it, retyping it so you can follow along better. So if prefix returns 0, then once again we get minimum length. And then we cycle through each letter again and compare it. And basically, if we cannot find that letter in our graph, so we're looking for W2 letter in our graph W1J, and if we don't find it, we can add it. So let me close this. Okay, then we'll insert it. And then we break, The next thing we need to do is basically go through all the letters in our visited array and run DFS. So first we pass to DFS our letter, we'll pass our graph, we'll pass visited, and our solution resolution. And then if there's a cycle, DFS fails, we'll return empty string. So let's create this DFS. We pass the character, our graph, which is an ordered map with a set of values. We'll pass also our visited map, hash map, and of course our solution string that holds the solution. All right, I'm gonna move this to this line here. All right, so the first thing is to detect a cycle. So to detect the cycle, we'll set this visited, the current letter we passed. If that equals to 1, that's a cycle because we're visiting it and we somehow accessed it again. So that's a cycle. If we already processed it, then we return true. And then we're starting to process it, so we set it to 1. And then for all the neighbors, we'll run DFS as well. Same thing. Return false if there's a cycle. Then we processed it already, the letter, so we set it to 2. Just typical DFS, topological sort. Then we'll add the result once we processed it. So the result is going to be backwards because with DFS, we're first processing the neighbors and then we append them as a result. Then we go back up the recursion and we add the parent to result. So it will be reversed result. We return true. And once we got our result, we finish the DFS, we know we need to reverse our result. And then we can return it. Because DFS, topological sort, like I said, we're adding the neighbors to result first, and then we go back up the recursion tree and add the parent, so our results are going to be reversed. So this reverse will reverse the string, and it will show proper order, such as W, E, and whatever. So now let me copy this function and run it in Leetcode again. There's an error. Line 36. I forgot to add the DFS function to the code. Oh, hold on. I made a mistake here. I forgot to... So one thing we forgot in this code is to add the check to make sure the letters are not equal to each other. Just like in the previous code we did before. All right, now let's copy the alien order function and our DFS function. Reset this code and run it again. Accept it, submit. Oh, I also put the break in the wrong place. You break right away when the letters are not equal. Okay. Let me copy the solution again. reset, submit. And there you go. That's 2 solutions with BFS and DFS. I hope you enjoyed the video. Subscribe to my YouTube channel, hit like and subscribe. Thank you.